it's a physics building on the other side of Stripa of the old towers. Just a straight line from here, straight over, I think. Should be easy to find. Today, I will start touching finite given volume a little bit. We'll come back to it later, so this is just sort of a first step. But also I'll use it sort of as a finish up of the finite difference as well. So sort of looking at things at once. But then the next step will be fast solvers. So here we start with nucleus. Maybe not today, but then definitely tomorrow. So we start last time a little peek into implicit methods as well. Implicit methods, dangerous, seductive. You can use a very big delta T, but know what you're doing. So I'm going to peek a little bit into the book by Ziege. The first two chapters is just overview. Chapter 3 covers finite difference. So actually we have done most of it already, so you can have a look at it. He has some polynomial fittings, some other schemes than just Taylor series. That can be worth just a peek. I haven't spoken too much about non-uniform measures. Of course, the methods, finite difference does apply there as well. You just have to do a lot of bookkeeping. So let's have a look. Should be here somewhere. 3. Here we go. Here we go. So he uses here in his book the same notation as Patanka. Patanka, he was quite famous. He wrote a book. I think you have it in the material. He only wrote one version of it, so it's definitely sort of the practical view into CFD. That's where the whole thing started, actually. So he uses the same notation as Patanka, using this generic unknown phi and this diffusion coefficient large gamma. The velocity here is sort of not necessarily the unknown. So it's sort of a way to linearize this advective term when the unknowns are the actual velocities, as it normally will be. But sort of not the same, sort of a way to cheat around this nonlinear term. But if you want to have sort of a little bit flesh into such a generic equation, think of the phis as the velocities, and this one then will be the viscosity. So it's sort of a starting point here. Time derivative has been removed, so steady state only. And then the basic concept, as you all know, discreticize your space and start using Taylor series, finding expressions for the derivatives, and then insert them into your PDE. And here, the central scheme is definitely sort of the best view of the exact solution here to finding a derivative at one single point. Using backward or forward schemes can be very different, dangerous indeed. You can get the total wrong angle out of it. So variables we have to use with care, of course. I won't go through all this. You have a lot of recipes here. This polynomial fitting, yes, it is an option, and yes, it works. There, sort of, you guess that your solution is smooth and nice and will be nicely described with a polynomial. Of course, that doesn't have to be the case. So choosing this as a basis for your schemes, I will put a question mark into it. So depending on the problem. So it's normally not that much used. Neither is finite difference when it comes to that. In practice, you always use an interval code, finite volume, finite element. But as I said before, we do this finite difference because here is where we can do any analysis, stability, arrow checking, and so on. As always with finite difference. Yeah. You can have a look at this if you like. Second derivatives, as you have seen already. And even mixed derivatives, yes, no problem, discretizing something like this. And actually you've seen it already in this Sula code, where we have some mix, maybe not mixed derivatives, but at least a mix of directions into the same stencil. Boundary conditions, they will always be a question in any code. Like in Sula, we use ghost cells, and they were updated sort of one step behind, so they were always one after the real-time development. It's an easy way to do it, but not so correct as if you reprogram your code to involve the boundary conditions directly. That's always better. Of course, then more work. You have to redefine or rewrite all the equations depending on what boundary you run. So that can be a little bit messy. When you need derivatives on the boundaries, if you don't want to use those cells, okay, then you really have no option. Then you have to go into your domain. So you can see here a couple of suggestions. You have to use then 1, 2, 3 points inside, or even here up to 4 points from the boundary value itself to get a derivative at point 1 here, where the first unknown are set. So that can be quite difficult if you want high accuracy on the boundaries. You have to use a lot of points inside your domain. Of course, a matter of bookkeeping, but it can be a little bit messy. Finding the equation system and then solve it somehow. And also here he uses Patankar's notation, center point P, and then all the neighbors. Here we use L for all the neighbors. That's okay. And also this one, Patankar as well. North and south, west and east. And in 3D you also include top and bottom. So that is his way of discretizing the space. And sometimes we are going to need a value here in between. Then he uses small letters. So for a cell around point P here, sort of your cell that you are focusing on, you're going to need values on the cell faces. And then it's a small w, small n, small e, and so on. We'll come back to that when you look into finite volume. Solving equation systems, well, that will be our next topic as soon as we're finished here. How to solve this one efficiently, quickly. Synchronization that we have looked for, and also consistency, and so on. Spectral method, that's something we have to mention at least. You should know what it is. And spectral methods, quite new actually, but not that much used yet. So you say you can represent any function here as a discrete Fourier series, and now it's just a question how many points do you need to describe it well. So it's a little dangerous with spectral methods. If you don't use enough points, it can be really bad. But if you have enough, an adequate number of cells, is definitely the best method. Much more accurate than finite volume, finite difference methods, but messy. You have a lot of math to go through here. So, interestingly here, it's a function of wave numbers, the effective, and including the additive and the real one. So the spectral method here behaves actually beautifully, while the central differencing schemes, they can follow a little bit, but sooner or later they will be way off. You also have a more modern version called finite element spectral methods. So you discretize your space into volumes, and then within each volume, within each element, you use a spectral code. Very efficient, very sophisticated, and very accurate. Tough to understand. But we have some people working in the numerical math department dealing with that one. So really interesting. Very, very good. If you use a pure spectral code, then you have the problem with your boundaries. They have to be periodic. So that can be, of course, a pain. And also, you must use a uniform mesh. That's not always so nice, especially if you are interested in, say, the vicinity of one wall, and then you want to go to infinity in the other end. It would be a bad idea choosing a spectral method, a pure spectral method. Okay, this just for information. Now let's have a peek at an example. It doesn't have that many examples in this book, so let's take the few there is. We have the original problem or equation here. That's then the advection diffusion equation, one-dimensional. No source term, no time derivative, hence steady state situation. And we want to solve here this equation from 0 to L. And then it's a question, how will our unknown phi behave? We have given the velocity field, then u is known, just a constant. And here assumed positive, then the boundary values for our phi goes from v0 to vl. Should go something like this if you don't have any transport at all. So now it's a question, what is this viscosity? That's what you can play around with here. And also, which way will he move, positive or negative? So moving here to the right and increasing or decreasing this viscosity, you can have quite a sharp behavior for the variation of phi in this domain. He operates here with a Peclet number. And the Peclet number should be defined down here. And of course you recognize this as a Reynolds number when you use the viscosity here. So the velocity scale, length scale, and then the diffusion coefficient. For this test case, we have an analytical solution, so we have something to compare with. So that's nice. So now doing the discretization should be straightforward, and doing some stability analyzers. It's a little trick question, isn't it? Talking about stability here, we don't have time in the problem. So where's the problem? Where's the stability problem? Let's have a look. So this was example 3, what was it called? 311. And the equation reads x derivative of OU phi, and then we have equals x derivative of gamma x derivative of phi. Like that. And now we assume mu is positive, constant, density is constant, and here then the diffusion coefficient also constant. So you can rewrite this equation here as x derivative of phi equals, and then you will have 1 over the Peclet number. What will it be? Well, we divide it out. Gamma, and then you will have here rho u, double derivative with respect to x. And there you see, you don't really have the Reynolds number as you should. You're missing a length scale. But if you now rewrite the equation in a non-dimensional form, so saying this x, you replace him with x divided by L. Okay, then you will have an additional L here. So if I do it like this, now the equation is in a non-dimensional form. That's the only trick. So this L comes from saying the x equals the real x divided by L. So formally then it should be like this. Saying that one is with that one. Making a center of a scheme. Let's say you call this a CDS, central differencing scheme. Okay, we have to use here a single derivative center that should now read something like this: I plus 1 minus phi I minus 1 divided by 2 delta x equals. This one then was, we could use the same Peclet number. I'm not capable of writing Peclet number, I always write Reynolds number. And then the double derivative should now read something like this: phi I plus 1, 2 times center point, plus phi I minus 1 over delta x squared. That's it. Now how to solve this, how to program this, or how to look at stability, if you should call it that at all. I mean, here you can solve this equation system directly. You write it on the matrix form, and then you'll see you will have a 3-diangular matrix system. But let's just see if we can get some stability or instability out of this. If you were to program it in an iterative manner, you have to pick one of them, put him on one side, and then throw everything else on the other side, and then reiterate many times to get the correct solution. And normally, with a central scheme, you will always focus on the center point. So just isolate this guy. That's all you have to do. Let's see, you have one dx disappears. And what will we get when we write it like this? Phi equal to. It will be a little bit tricky, won't it? We have to multiply up here, the clear number, divide by delta x. Let's see what we get. Then I have a factor 2 here. So it should be something like this, delta x up. Clear up divided by 2, and then I will have these two guys, phi plus 1 minus phi minus 1. He's going to be negative, like that, and then these two on the other side, negative, and change sign, so they should be positive, and they will just be phi plus 1 plus phi minus 1. And then I must divide everything by 2, mustn't I? Isn't that correct? I think so. Let's try it. Take one of these guys, phi plus 1. What should he be multiplied with? Well, I have 1/2 on both terms, so here I will have 1/2 plus from him, minus, and then I get the clear number, delta x, and then I will have 4 here. Right? And then the other one, phi minus 1, should be multiplied with 1/2, and then I will have minus reads plus, declare delta x over 4. There we have it. So that should now be my iterative recipe, algorithm. You just do this for all i's many times, and then he should converge towards a solution. Well, is that the case? Now check the max-mean method. The sum of the coefficients should be 1. And yes, they are. Add these two together, you get 1. Hence, you could use the method. Next demand. All coefficients positive. You write it like this. Sum of coef is 1. Okay, we can use the method. All coefficients should be positive. Well, the Becquerel number here, we can say is positive because I choose a positive u. Then the last coefficient is no problem, but here I have a minus sign. Okay, so if all coefficients is to be positive, that means multiply here with 4, so you will have 2 have to be bigger than the Becquerel number multiplied with delta x, like that. Now, what will that mean? Well, remember my x here, that is non-dimensional distance. So that's actually the real x divided by L. So if you insert here, what do you get? You have the Becquerel number, and that is rho UL over gamma, and now multiplied with the real delta x, delta x wave by L. So then you see, by just multiplying my non-dimensional delta x, I get the local Becquerel number. I get Becquerel based on delta x, not on L. So the local Becquerel number has to be smaller than 2. That is what he is saying. If you now say that this is the viscosity, then we have concluded here the cell Reynolds number has to be smaller than 2. So choose gamma equals viscosity. That means the cell Reynolds number based on delta x has to be smaller or equal to 2. Quite famous result. And to say the least, a real pain. Because the cell Reynolds number, it can quite easily become much bigger than 2. If you put in a real viscosity here, that's easy to see. So this is actually a demand for spatial resolution, nothing to do with stability and delta t. It's a criteria for delta x. Everybody with me on this one? That's okay? So now let's see how the code behaves. Yeah, one thing. To find this stability criteria, I sort of designed an iterative scheme here from this discrete version of my equation. Of course, this one's a one-dimensional equation system here, very easy to solve directly, but you will still have the same stability problem, as you will see. Yeah.
I was wondering how the max-min method is applicable here, because
yeah,
you're not exactly stepping forward in time, right? So
no.
This is a matrix system, and you could in principle solve the whole thing on paper once.
Yeah, that's
So
what I'm saying.
Couldn't you then violate this?
Yeah, so you could have solved this one directly with a Thomas algorithm or something. I mean, it's very simple equation system. Nevertheless, this is still present, actually. Even though I'm not doing this iterative procedure, which we sort of have to do if we want to use this max-min method, but the criteria still apply.
But if I violate this criterion,
yeah,
and kind of solve this matrix system like just by hand,
yeah,
I would get a solution, right?
no, it will still blow up. I'll show you. I'll show you. Let's see here, back to the problem. Original equation with the analytical solution, the Becquerel number. So now just remember, you multiply this one with delta x, then you automatically then get the local Becquerel number. How he has discretized it, I don't want to go into this, you can have a peek for yourself. Let's jump to the code. So here we have his first case, only 11 points. And I choose a global Becquerel number. Then I print it out, and here also I now print out the local Becquerel number, just multiplying with the x. So this is the cell Reynolds number. Setting the left and right boundary values, comparing here with the analytical solution. And then for the CDS scheme, I now write it as I've written it here. This is sort of the original that we have on the whiteboard. rewrite this on as an equation system, finding the coefficients, and then solve it directly using a TDM algorithm, Thomas algorithm. You just, so it's a direct method here. And then print the solution. The UDS, we can have a look at that one afterwards. Let's just try to run this. And we get something like this. Same behavior as Fritziger gets in his book, of course. So the exact solution, the red one, starts with 0, and then he should go to 1 up here. And the blue one, that is now our central scheme, as you can see, he is really way off the nose. So clearly not a good idea. And the reason, you can see here, the Peclet number was 50, but using 10 cells, okay, then the Peclet number is 5. So it's just too big. And to get a better one, well, you have no choice. You need more cells. So how many do we need here? 40 or something? Looks a little bit better. And now the cell Reynolds number is smaller than 2. Then the scheme will be okay. So here, the solution, exact, and the blue one follows it very nicely indeed. Let's try to push him a little bit. 31. Yeah, we are still below 2, so this should still be a nice one. And it is, not so bad. And going to 21. 2.5. That's a little bit too much. Let's see how the solution looks. He's beginning this physical behavior program. And this is all with the direct method. So you can't sort of get out of this. Cell Reynolds number has to be smaller than 2, sadly. What happens with an upwind scheme? EDS. So now we do I do a UDS directly. What's the difference? Not much. A UDS, well, first of all, then we really have to be certain that the transport velocity is then a positive one. It's only this advective term that you can choose an upwind scheme. So it's here that we have to do something. And now I say small u is positive. Okay, then I will remove +1 here, and I will remove the 2. That's the only difference in the stencil. Here, then I use the upwind differencing to create a first order derivative, and then divide it by one single delta x. So what will happen in this algebra? We will get rid of the 2 here. And here I will have only E phi I and not phi I plus 1. But then you see we should do the calculation again. Because now I will have a sort of a different stencil here. Let's see. This guy, he actually belongs on the other side, so we have to recalculate this a little bit. Phi I. We should then be multiplied with 1, as we have here. Then I have minus something, but on the other side he should be positive. And that should now be something like the clear number delta x divided by 2. So that is P multiplied with delta x, which is actually the same as the clear number based on delta x divided by 2. And then we have thrown him on the other side. Equals. And then we have here I plus 1 should now be multiplied with what? Well, now I don't have the plus 1 here anymore, so I only have this guy. So he's only multiplied now with 1/2. Right? And then the other one, I minus 1, should be multiplied with what? Well, he has also 1/2 here, and now I also have contribution here, but that's minus minus, so that's plus. So I should get this one back. One half plus delta x, but then not divided by 2 there, but I have a number 2 here, so only 2. There we have the stencil. Okay, let's try max mean again. What's the sum of the coefficients? Well, they will be 1/2 plus this parenthesis here. So the sum of the coefficient here looks like 1 plus half of the self-Peclet number, but we have to divide by that afterwards anyway. So the sum of the coefficient is 1. Okay. When you write this one on the form, Ci equal to. So yes, you can still use it. And now you see the demand, all coefficients positive. And yes, unconditionally. So now you can choose any delta x. So unconditionally stable. So according to the stability, the first order Rockwain scheme looks like a brilliant idea. Any questions to that one? That's okay. Tiny difference, but quite a different turnout. So you can actually see it here already that because it's 21 cells, our central scheme starts really to fail. The green one, that's the first order Rockwain scheme, the UDS. He is giving a solution, but he is not actually giving me a solution for the clear number 50 as I wanted to. This is actually more like the solution for the clear number 18. So you think you are doing one Reynolds number, but actually you are doing something completely different. So that's the danger here. He adds a lot of viscosity into the problem. So how far can we push him? He should be unconditionally stable. So if we go, say, 5 points, so now you see the UDS scheme is really into trouble. And the UDS, first order Rockwain, well, he's still stable. He sort of behaves in the right manner, but very differently from the analytical solution. Of course, with only 5 cells, it's impossible here to find this sharp gradient. It's not possible. You have to resolve the behavior here, you need some cells here to get a correct result. Of course you do. So, also shown in the book, I think, it's possible here with this problem to stretch the mesh, since you know here is where the interesting things happen. Here is where you have a sharp gradient. Then you use very small delta x's here, but then you can make them bigger and bigger and bigger because nothing is happening here to the left. Yes, that's quite possible. And you should get a quite nice result anyway. Let's see if that is the case. Yeah, so here he has used just the 11 points, but with a non-uniform mesh, just stretching the mesh. So to the left you have the central scheme, and he fits it now very nicely indeed. Although the average cell Reynolds number here was 5, but you have quite small cell Reynolds numbers in the area where you have the sharp gradients. For the upwind scheme, well, it still really doesn't help much. Quite a lot of viscosity has been added into the. Any, yeah, we'll say something about that one as well. It's possible here, since you have the analytical solution, defining an anode and then playing around with different measures and see how they behave. So a second order accurate code should then have a slope of 2. First order have a slope of 1. And yes, of course these schemes will follow these theoretical slopes quite nicely. If you have small enough delta x. Too big delta x, then something strange will happen. Any questions to this one? That's okay. Then we take a break.